Well, 2 long nights in a row. Hopefully, this is not going to be another one. We'll see. I have my caffeine. All right, we reach fresh air. Emerge near the base. Spits of lava. Commands of lava, speed at which it cools. It might be forming obsidian. Cooling rate should be based on the surface area of the lava droplets. So you take a quick scan of the droplet as it flies past you. So quickly the lava is moving. The scan isn't very good. Its resolution is quite low, and as a result, approximates the shape. I guess that's it. Alright. Approximates the shape of the lava droplet with a 1 by 1 by 1 cubes on a 3D grid. To approximate the surface area, count the number of sides of each cube that are not immediately connected to another cube. So if your scan were only 2 adjacent cubes. Okay. What is the surface area of your scanned lava droplet? So this is all one droplet. That's a lot of cubes. Um, Surface area of the thing. Well, the easy way to solve this is to just throw them all into a hash table, right? And then evaluate each. I guess that would probably work. And my puzzle input about 2,800, so that's not excessive in size. Um, let's do this. All right, so that'll give us a hash set of tuples, which should be fine. Although, as we learned yesterday, tuples as a hash set key isn't necessarily good, right? Oh, no, they're fine. Okay, they have the same hash code. Oh, wow, that font is really small from yesterday. I think, yeah, that's what it normally is. Okay, good. All right, so yes, those are fine as a hash set key. Yeah, So then basically what we're going to do is we're going to say for each var cube in data, we'll call them pixels. How about that? So every one of these has 6 sides, right? If, let's see, data contains pixel x minus 1, pixel y, why does it say pixels? Pixel y, pixel z. So if it doesn't contain that, 1, 2, 3, 2, 1, 0, then result plus plus. All right, we'll do this 6 times. So you're now x plus 1. Right, and so you guys are now x, right? And you're y minus 1, y plus 1, z minus 1, z plus 1. Let's see what this results in. 64. Okay, let's try the real data. Where'd the real data go? The real data is gone. Come back, real data. We miss you. Let's see what happens here. 4314. Okay, next. Something seems off about your calculation. The cooling rate depends on exterior surface area, but your calculation also included the surface area of air pockets trapped in the lava droplet. Instead, consider only cube sides that could be reached by the water and steam as lava droplets tumble into the ponds. The steam will expand to reach them as much as possible, completely displacing any air on the outside. In the larger example above, exactly 1 cube of air is trapped within the lava droplet. So the exterior surface area of the lava droplet is 58. So that means, I think, that we just take the extents and scan them. Right, so after this, so you're going to start with results from part 1. Then we're going to do min x is data, select the pixel, the minimum value, and then your max x is the maximum value, min y, max y, min z, max z. You guys are going to scan z and y. And I think what we do is we scan everything and say for every, let's see, so that's 58 because that's 6 less than 64. So every one of these, when we scan, we say if you're surrounded on all 6 sides, then your 6 go away, right? So let's do this. For x is min x, x less than or equal to min max x, double plus x. Oops, we'll do that 3 times, not 4. Your y and your z and your z and your y, your y and your z and your y and your, Telesense helping me too much. Thank you. Okay, so for every one of those, we're basically going to say this again. All right, we're going to say if, let's see, so we don't need pixel dot in any of these. whatever. You're not helpful. Go back. Yeah, whatever. Okay, so what we're looking for here is if that's true, that's true, and that's true. All right, then result minus equals 6. I think that's all that I need, right? So you're going to give me back 58, 52. Interesting. In the larger example above, exactly 1 cube of air is trapped in it at 225. 225. Exactly 1 is trapped in there at 225. Okay. Line X, Y, Z. What's the other one we're finding? 222. Oh, we probably have to make sure that we need to do this, which is we need to make sure that we are not one of these. Oops, not there. You're going to go down here with everybody else. So we need to make sure that we are not there, because 222 is one of the data contains, all right. Okay, that's 225, 58. Okay, let's try the real data. See what we get. 4074. 4074. Not the right answer. Interesting. I did read it correctly, right? 4074. 4074. There's no way to be surrounded on all 6 sides and not be inside, right? Let's do this again. X, Y, Z. So that's a pretty small list. Give me a notepad. Let's put our list over here. I'd really like to see this list sorted. That would make it easier, wouldn't it? To see this list sorted. Let's see. What would be the easiest way to sort that? Anyway, let's go looking for some of these to make sure that we're not 468 is not in there. 485, I'm sure, is not going to be in there. 485 is not in there, right? And then the real question is, why would any of these be Min-max, 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 x, y, z. Well, let's do this. Console right line. Data cube is min x to max x, min y to max y, min z to max z. Don't think the size of this thing is that big, right? 1 through 20, 0 through 21, 0 through 21. We shouldn't see anything that's in 1 or 20. We shouldn't see anything that's in 0 or 21. And we shouldn't see anything that's in 0 or 21. And that is true. We don't see any of that. So, because of course that would definitely be the outside of the cube, for sure. What am I missing here? We are not. And all of those are there. And we are surrounded. Is there something I'm missing in the description of this? Exterior surface area calculation also includes the surface area of air pockets. Only cubes. Oh. So, yeah. All right, I think I understand. There's probably some of these that are next to each other. Let's see. Right, none of these are completely isolated. But there could be cubes that are next to each other. Right, on the interior. So you basically have to go outward in every direction until you hit the edge, in which case you're not inside, or you hit an edge, in which case you're inside. But you only get to count the direct, you only get to count the surfaces that you are directly against. Okay, that makes sense. All right, so if you're not in here, then we got to do something with this, right? So find edges. All right. Okay. So if you're an air pocket, we want to go in each direction and look for an edge. Right, so what is the easiest way to do this? Would be x2 is x plus 1, x2 is less than or equal to max x, double plus x2. So let's see, found edges is 0. All right, so we go that way and we say if data contains x2, y, z, then we found an edge that way. All right, so we've got to do this in all 3 directions. So let's go this way, -1, and you need to be greater than or equal to min x and then minus, right? So that search is in x, then that search is in y, and that search is in z. So we need y, 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 y. y, 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 this is x and y2, and then z, 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 z. And then this is the direct edges. We also need to know that. So that's a found edge. And then we're going to say if x2 is equal to x minus 1, then that's a found direct edge. Okay. So I basically need this in here as well. Okay. So if you're right on this edge, oh, and once you found your edge, you can stop looking too, of course. So if y2 is y minus 1, right? So y2 is y plus 1. Whoops. z2 is z minus 1. z2 is z plus 1. So then we're going to say if found edges is 6, then result minus equals found direct edges. So only discount the edge that you directly see. Found direct, is it found direct edges or no? Yes, because we counted you. Yeah, that sounds right. All right, let's go back to the old data. So we should still see console right line x, y, z removed, found direct edges, edges. Let's do that. So data cube is blah, so we didn't find anything. So something's wrong with our logic here. What is wrong with our logic? So if you are not in the data set, then we're going to go looking for your edge to the right. Right, so let's do this, console right line. Edge for x, y, z is x2, y, z. And this is a right, so that this will say console right line, direct edge, right line, indirect edge. Right. Plus 1. Yeah. Fine, take all that. So if y2 is y minus 1, your x and y2 And your y2y plus 1, your x and y2, and then your z minus 1, x, y, z, and then your z plus 1. Okay, let's see if we can figure out what's going on here. So here's our 225. Interesting is that 225 never found a direct edge anywhere on the sixth side. Why is that? Two, 5 never found its direct edge. I can sort this data by hand now. 2, 3, 2, 1, 2, 2, 3, 2, 2, 2, 1, 2, 2, 3, 2, 2, 4, 2, 1, 5, 2, 2, 6, 2, 3, 2, 3, 2, 2, 3, 2, 5, 2, 3, 5. So you're telling me 225 previously hit this. So there's 224 and 226. So 215 and 235, that's the other direction, right? And then that should be 226 and 224. Oh no, I did that already. 224, 226, so it must be 325 and 125. So we should have found each one of those. Something's wrong here. So that's a double minus and that's a double plus. We go backwards. Right, so let's set a breakpoint here with condition on 225. X is 2 and y is 2 and z is 5. Okay, so we can figure out what's going on here. Okay, so 225, we have no edges, we have no direct edges. So x2 is going to be 1. Right, so x2 is 1, so we have 1, 2, 5. So that's there, so that's that edge, and it's a direct edge. And now we've got 3, 2, 5, which is also there, and that's a direct edge. And now we've got 2, 1, 5, right? 2, 1, 5, which is there, and that's a direct edge. Now we've got 2, 3, 5, which is there, and that's a direct edge. And now we've got 2, 2, 4, which is there, which is a direct edge. And now we've got 2, whoa, we didn't even get in there. Max X is, oh, Max X, whee! All right, there we go. 64, still 64. Although, all right, 1 and 3, 1 and 3, 2 and 4. What did we do wrong here? Max Z. That should have definitely been the thing. Okay. Still not sure what's going on here. Z2 is Z plus 1. Z2 is less than or equal to max Z. Oh, this is min Z. max y, min z, max z. Is that y? No. But I'm definitely going to scrutinize this. X minus 1 min x. X max x plus y min y minus y max y plus z min z minus z max z plus. And this is backwards. Jeez, oh Pete's. 58. Okay, yeah, let's get a bunch of console write lines out of here. All right, every console write line, please become a / console write line. We got 50. Ugh. Edge for blah, edge for blah, edge for blah. Also, every console write. This is really what it meant, right? Which is every console write now becomes this. Which is ugly. All right, fine. Let's just do console write. You guys are like, why is he wasting so much time? I'm honestly, literally just trying to be optimal here and failing hard. Because of all these else's. And we stopped printing out results. 58. Back to the original data, please, which is now gone. I don't know why it does. Oh, yeah, I know why it does that. Of course, because I sorted this data. Let's go get my puzzle input again. Put it here. Give me a number, 3319. Oops, I was already there. 3319. Also not the right answer. I mean, it seems like the right answer. Hmm. Nobody should be removing, well, yes, things can definitely remove zero edges, because if they were never, wait a minute. Yeah, things can definitely remove zero edges, because if they're like just trapped in the middle, right, then they would not have contributed any edges anyway. There's only, for a given interior edge, there's only one cube that could ever be removed. Right. I've got an idea. Let's make sure there's no dupes. All right, which is, let's do this. Remove edges is a new hash set of XYZ, right? Of XYZ. And then we'll say potential edges removed is also a hash set of XYZ. And then every time we, let's see, direct edges, we'll call this direct edges. And then we don't need to count those anymore. Instead, we'll put you in the direct edge. Direct edges add x2, y, z. Whoops, you're an edge though. You're still an edge. You're just not a direct edge. We don't care about direct edges anymore. Oh, you're already done up there. Don't be dumb. So you're also x2, y, and z, right? So your x, y2, and z, right? And then your x, y2, and z. And then your x, y, z2, and your x, y, z2. Get rid of all these console write lines. They are not helping anymore. Whoops, bring the break back. Okay. Direct edges count. Direct edges. I was thinking about putting these in a hash set and making sure they're in a dupes, but actually you can have a dupe, right? You could have a dupe from one side and then the other. This should give us the same answer, though. Oh, it gives us a different answer. That's interesting. 4314. That's part one. Oh, that's because we didn't remove it. Okay, right. Result minus equals direct edges count. I must have inadvertently deleted that code. 2439. I don't remember. That doesn't sound like the one I put in there before. No, not the right answer. 2439, not the right answer. I don't think this is going to matter. Like, I don't think this is an off by one problem. 2439. That's not going to make the problem any bigger. Okay, so 2439, that's fine. So that is not a contributor. It's not possible to just have one that's in the middle doing nothing, right? I don't think. but I am curious. So what if I did a dictionary here to int, right? And then when we remove this, we basically say if not removed edges contains, we do this, for each var direct edge in direct edges, if you do not contain that direct edge, because that's our XYZ, right? So that contains key. So if you don't contain this direct edge, then we're going to say removed edges of direct edge is 1. Otherwise, removed edges direct edge double plus. At the end, is there anything that got all 6 of its edges removed? That's what I want to know. Removed edge in removed edges, where the value is 6, greater than or equal to 6. That would be interesting too, wouldn't it? Console right line cube at removed edge x, removed edge key. Actually, you'll just print it out. Appears to have removed too many sides. KVP value. Whoops, removed edge value. Let's see if we get any of those. So that's interesting. We never got more than 6, which is good, but what it would imply is that these things are completely isolated, right? So for each one of these, I kind of want to look at the data and say, are you actually isolated? Pixel, comma, count. Result is 0L. Result 2. So this is result 2, 2, 2, 2, 2, 2. If result 2 is not equal to result, console right line, not equal to, sorry, not equal to count. We have a mismatched count for pixel. Expected count, but verified result 2. So we definitely have a bunch of 6s where they were completely removed, but they're like floating. They're floating inside. Cooling rate depends on exterior. In calculation also included the surface area of air pockets trapped in the lava droplet. I wonder if I just add those, whoops, my window moved there a little bit. I wonder if I just add those back, if that is the answer. Right, and then we just do result plus equals 6. Give me those back. 2565, is that what it's looking for? 2565. That's not what it's looking for either. Please wait 5 minutes before trying again. Okay, so that's not what it was looking for either. But there is something weird about these floating pixels inside. But we definitely would have counted those. I mean, we're using the same logic here that we used up there, so we definitely would have counted those floating pixels. And they probably shouldn't be counted. I don't know if they should be counted or not, but I think we tried it both ways and ended up with the wrong answer. But it definitely feels like this is really what the problem is something in here is the problem. These floaters, 2439. 2439, wait a minute. When I had this in here, what was it before? What was it after that? 24, 25, 65, okay. And that's because every one of these contributed. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 of these. So 2439. 2439, well, let's see, 21 times 6. 2439 is 2565. That's definitely the other answer we got. What if we go about this a different way? Right? What if, I mean, I generally like this strategy of going out, but what if we went at it a different way, which is to say, you're only allowed to have a surface counted if the direction that you go in has nothing else. Like this whole removing things, this obviously isn't the answer. And we don't want to start with get part 1. Right, so instead, let's do this, which is we're going to look at every pixel and we're going to say, if you are one of these, then we're going to go look for an edge. Right, so we're going to assume that we should count all of your sides unless we find an edge in any direction. At which point we also want to break. Right? Let's try this instead. Yeah, you should be like that. Thank you. Actually, you're already there. So we're just going to do this, and this, and this, and this. And we don't care about any of that. We should just get a number. All right, let's go back to our old data. Let's make sure we get 58. And we got 50 this time. Okay, let's see. Hmm. Let's do this. Old result is the result. Then we'll say if old result is the result, then we want to say excluded no, this logic isn't right. We need to make sure that we find at least, right. We need to make sure we find at least one outside edge. How do we know we find at least one outside edge? You can't just go in a straight line because the outside edge could be as a result of something else. And I'm reluctant to explode this with another set of loops. But in essence, that's what it is, right? It's like, hey, I found something. Is it on an outside edge? Which is, you know, which of its edges are on an outside edge? So you have to check in all 6 directions. So it's kind of like you're trying to trace a path to air from an edge. So what is the easiest way to do that? The easiest way to do that is to start. Yeah, is to do this. Okay, so we'll do this. We'll write it in terms of this. If can find outside air for x minus 1, y, z, result plus plus. It's plus 1, y minus 1, y plus 1, z minus 1, z plus 1. And here, I think we're going to need to use some cache. That's what it feels like. All right, 1, 2, 3. I missed parentheses all around here, didn't I? Okay. So we need to find can find outside air of our lambda. And we need an outside air cache. So we're going to say outside air cache is a dictionary of lambda to Boolean. So if outside error cache, try get value. Try get value for the pixel. Out our results. Return results. Okay, so that's first part. Now, if data contains the pixel, then we're going to say outside error cache of pixel is false. And we're going to return false. Otherwise, we're going to return can find outside error of pixel x minus 1, pixel y, pixel z, and plus 1, plus 1, and y minus 1, y plus 1, z minus 1, z plus 1. Now we have some other exit conditions as well, but in order to get those, we're going to need the mins out here. All right. So there's that. We're going to say if x is pixel x is equal to min x, or pixel x is equal to max x, or pixel y is equal to min y, or pixel y is equal to max y, or pixel z is equal to min z, or pixel z equal to max z. Then we're going to record this as true. This is also result is equal to this. And then we're going to record this result in the cache and then return it. We could also do this result is false. We do the else. All right. You do this, else if that, and the result is true, else this. Okay. Now we're putting it into cache every time and we're returning the result. I think that should work. So we're back on our old data. Yeah, if we get 58, then I guess I trust it, right? Okay, we loopity, Stack Overflow. Okay. So we're going to say every time, we're going to go from min to max, min to max, min to max. If you're there, we do less than or equal to, because of course we're going to come in with some that are already greater than or equal to, right? Because we're already going to exceed issues. You know, if we don't increase the mins and maxes, that is, because we know the mins and maxes would be outside air. Does that help our loop? Now we get 58. Okay. Now we have stack overflow. That doesn't make sense. Why do we now have a stack overflow? If I hit this in a debugger, stack overflow is here. Outside air cache. We're looking for, what is our pixel is 257. Why is 257 so problematic? We have outside air caches. We have lots of them. We must be sort of sitting in a loop. Yeah, like an interior space loop. How do we solve this? Yeah, how do I solve this? Yeah, how do I solve this? Like I can't, I'm doing it recursively, which means I would need to keep a list of places I've visited and only try and visit places I haven't already visited. Is that right? So hash set of int x, int y, int z visited. And if you don't give us one, you get a new one. No, if you don't give us one, we'll give you a new one. Yeah. What am I missing here? It's like that, isn't it? Now what? What? God bless America. I really need this caffeine. I really need it. Put ourselves in the visited list. Put ourselves in the visited list here. And then we remove ourselves from the visited list here. Whoops. So we assume that any place that we've already visited is probably safe, right? If visited contains this pixel, then we'll just return true, right? Is that going to get us out of the loop? I think that'll get us out of the loop. 452. That is a very small number. 452. That is also not the right answer. That was a very small number. But if you're only measuring the outside, that sort of makes sense, right? With the old data, that'd still give us 58. Yeah, not surprising. What I really want is, let's copy this somewhere else. Let's make a set of data that has the cube problem. What is the easiest way to do this? So we'll do 1, 1, 1. 1, 1, 2, 1, 1, 3, 1, 1, 4. All right. And as long as every edge has at least a 1 on it, then it's totally the outside edge. All right, 2, 1, 1. 2, 1, 2, 2, 1, 3, 2, 1, 4. 3, 1, 1, 3, 1, 2. 3, 1, 3, 3, 1, 4. 4, 1, 1, 4, 1, 2, 4, 1, 3, 4, 1, 4. Let's do now, let's see. We need to do the middle, right? Let's be 1, 2, 1, 2, 2, 1, 2, 3, 1, 2, 4. 1, 3, 1, 1, 3, 2, 1, 3, 3, 1, 3, 4, 1, 4, 1, 1, 4, 2, 4, 3, 1, 4, 4. So that's a 4 by 4 cube that's hollow on the inside. Right? Is that? Yeah, we're not done. Or we're not done here, right? 2, 2, 1. 2. Can't do 2, 2, 3, but we can do 2, 3, 1, 2, 4, 1. All right, and then we should be able to do 3, 2, 1, 3, 3, 1, 3, 4, 1. And then down here we've got 4, 2, 1, 4, 2, 4, 3, 1, 4, 1. Thinking about this, right, it would be 16 and 16. And then 8 and 8. 16 and 16. 8 and 8, 4 and 4. 16, 16, 8, 8, 4, 4. I should have 56 of these, and I don't. What did I do wrong here? So that's the top side. The bottom side should look exactly like that, except 4. Oh, right. Every side has to have at least a 1 or a 4. That's what it is. So that's my 8 along the 2 axis. 3, 2, 1, 3, 2, 4, 3, 3, 1, 3, 3, 4, 3, 4, 1, 3, 4, 4. That's my 8 along that axis. Hold on, 4, 2, 1, 4, 2, 4, 4, 3, 1, 4, 3, 4, 4, 4, 4. Except you should be able to do everybody because you have a 4, right? So 4, 1, 2, 3, 4, 2, 4, 2, 2, 4, 2, 3, 4, 2, 4. We've got 4, 3, 1, 4, 3, 2, 4, 3, 3, 4, 3, 4, 4, 4, 2, 4, 4, 3, 4, 4, 4. Okay. So that's 1, 2, 3, 4, 1, 1, yeah. 1, 2, 3. So that's my 16. Is this my 16 down here? Yeah, 40, 55. So that's the bottom. 2, 1, 2, 2, 1, 3, 2, 1, 4, 2, 2, 1. 2, 2, 2 is no good. 2, 2, 3 is no good. 2, 3, 1, 2, 3, 4, 2, 4, 1, 2, 4, 2, 2, 4, 3. Right. There's my 12. All right, there's my 8 and my 4 that I was thinking of. And so then this one down here now also needs to be 3, 4, 2 and 3, 4, 3. All right, so that is now the sum total of my interior cube. 56, that is what I wanted. So when I run this, I've got 120 on the outside, right? Because I've got let's see, along each edge, I've got 16. So 16 times 6 would be 96. So 96 was my exterior only answer. So that's good. 120. I'm gonna like this logic. The step 1 logic is unimpeachable. That logic is fine. So that's 96 on the interior because it's only the exteriors. So if I was to take away 1 cube, like take away 2, 1, 2, right? Well, what would that look like? You just take away a cube that's sort of in the middle. That would take away 1 surface and add, oh, well, that's interesting. Yeah, I mean, if I put a hole in the middle of it, if I put a hole in it, then the 2 numbers are the same, right? So if I take away 2, 1, 2, oh, that's interesting. 122 and 99, that's not what I expected. Because I would have expected 122 by taking that 1 hole away, right? Because everybody should be able to find air by way of the hole now that exists. But let me take a hole. Let's see, what is a, I mean, any hole will be fine as long as it's not in a corner. All right, 212 is not in a corner because it's only got 1 or 4. So it's not in a corner. If I take a corner away like this, yeah, it's exactly the same. It's still 96 inside. You can't escape from the corner, but you took away Yeah, just by chipping that corner out, all you've done is actually that's weird. Chipping that corner out. Why does that? Oh yeah, of course. Because the number of exposed sides doesn't change just because that corner has been chipped away. Yeah, that makes sense. But if I take a hole out, which would be like 1, 2, 3, right? Then what you've taken away by taking a hole out is the exterior and interior edge. So that's why we go from 124 to 122. But why don't we go to 122 for everybody? Because everybody should be able to escape by that hole. All right, this is the source of my problem. Everybody should be able to escape by that hole. So let's set a breakpoint at something we know is air. Right, so let's set a breakpoint at, let's set a breakpoint here at like 2, 2, 2, right? Pixel X is 2, and pixel Y is 2, and pixel Z is 2. So why can't you find outside air? First of all, are you in the visited cache? You shouldn't be, right? We're brand new. So here's 2, 2, 2. Okay, so the outside air cache obviously has not contained 2, 2, 2 yet. So we've already found some falses, like 1, 2, 1 is a false. Why is 1, 2, 1 a false? Our min yeah, why is 1, 2, 1 a false? Okay, I want to find that out. Because you're on the edges. Why is 1, 2, 1 false? Okay, so we're looking at 1, 2, 1. Outside air cache has almost nothing in it. Okay, so min x is 1. Pixel x is 1. So that's less than or equal to. So the result here should be true. We're not in a visited list because there is no visited list yet. We don't have a result. You're not in the visited list. You go in the visited list. Oh, I see. 1, 2, 1 can't find air because it isn't air. Yeah, never mind. I was thinking about things that were incorrect. By the way, we have values in here that found air, right? We definitely found air from 0, 1, 1. Yeah, that makes sense. That's an outside edge. All right, that's outside the cube. So all the trues right now have zeros on them. All right, so our path out. So what is so we removed 1, 2, 3. So we should be able to find our path out via 1, 2, 3. Which I guess means we should look at 2, 2, 3 because that's one that's gonna come up, right away. So let's do 2, 2, 3. We're not in the cache yet, I assume. All right. And we aren't in the visited list. Okay. We're not a pixel, that's true. We're not on the outside, that's true. So now I should be able to visit 1, 2, 3. Right, so now pixel is 1, 2, 3, which is the one we removed. Do we have 1, 2, 3 in the cache? Guess we'll find out. We do, and the result is yes, you can find outside air. Oh, is this? Actually, these should be ors, shouldn't they? These should be ors. You dummy. All right, so now you're 120. Oh, you're 120 and 120. That's not true either. Because we need to remove all the inside air now with the data where it is. So let's do two, 2, 2 should never be able to find outside air. Wait a minute. Yeah, this logic is reasonable, but I've implemented it wrong, and I'm trying to figure out what is the answer. This needs to be false, just so we stop looking that direction. Is that what the problem is? Yeah, that needs to be false. Okay. See what happens when we try it with the real data. 2444. That's the answer. Okay. Wow, that took way longer than it should have. But I'm glad for it to be over now. Yeah, so the end result was basically we had to go try and find a path outside. So given a piece of air that's inside, is it connected to air outside? Right? And if it was, then we needed to remove every side that was connected to outside air, or we needed to add every side that was connected to outside air. So basically we looked at every pixel that had lava in it, right, and said, for every one of your edges, if you can find outside air, that edge counts. So there we go. And obviously coming up with my own data set here with a hole in the middle that I could then poke a hole in was kind of the clue to get the right thing. The data that they gave me was not sufficient, but that's the way these go, right? The sample data is always incomplete by definition. So there we go. I think that's going to be it for today. So we'll see you tomorrow. And let me tell you, I'm very happy to not have to do 4.5 to 5 hours on this one. See you tomorrow.